Hello students, welcome back. Today we'll see some extra questions related to chapter number 4, that is principle of mathematical induction. Okay, so let's start. For every positive integer n, prove that 7 raised to n minus 3 raised to n is divisible by 4. Okay, so let's check first for p of 1. 7 raised to 1 minus 3 raised to 1, that is equal to 4, which is divisible by 4. Hence, P of 1 is 2. Now let P of k be 2. So now it is divisible by 4. I will write it down 7 raised to k minus 3 raised to k, that will be equal to 4 lambda. So that means 7 raised to k, that is equal to 4 lambda plus 3 raised to k. Number 2, this as number 1. So we will be using equation 2 for proving p of k plus 1. For p of k plus 1, we have to prove 7 raised to k plus 1 minus 3 raised to k plus 1 is divisible by 4. Clear? So let's take 7 raised to k plus 1 minus 3 raised to k plus 1. This will be equal to, instead of 7 raised to k plus 1, I can put 4 lambda plus 3 raised to k. 4 lambda plus 3 raised to k minus this 3 raised to k plus 1. So I will write it down. 4 lambda plus 3 raised to k minus 3 raised to k into 3. Clear? So this will, sorry, there is a mistake. Here it's 7 raised to k plus 1. So it will be 7 raised to k into 7 minus 3 raised to k plus 1. Yeah. Now instead of 7 raised to k, I can put 4 lambda plus 3. 7 into 4 lambda plus 3 minus, instead of 3 raised to k plus 1, I can write it down 3 raised to 1 into 3 raised to k. Yeah, so this will be 7 into 4 lambda plus 7 into 3 minus 3 into 3 raised to k. Clear? So I can take here 7 into 4 lambda from 7 into 3 and this. I can take this common. Sorry, here it's 3 raised to k. So from this and this, I can take 3 raised to k common. So 7.4 lambda plus 3 raised to k common, it will be 7 minus 3. 7 minus 3, that is 4. 7 into 4 lambda plus 4 into 3 raised to k. So 4 will be common. So 7 lambda plus 3 raised to k. As I have taken 4 common, I can write it down, which is multiple or divisible by 4. Let's leave this as 3. So from 1, 2, and 3, according to principle of mathematical induction, P of n is true every n belonging to n. Clear? Just note down this question. Let's see other one. Prove that 1 plus x raised to n is greater than equal to 1 plus nx for all natural number n where x is greater than minus 1. Okay, so now let's take for p of 1. 1 plus LHS I will say 1 plus x raised to 1 and RHS 1 plus 1 into x. So both are same. LHS equal to RHS. So I can write down 1 plus x raised to n 1 is greater than equal to 1 plus 1x because it's equal sign. Okay. So p of 1 is true. Should I will write down equal, right? And the question includes equality sign also. So p of 1 is true. Now let p of k be true. This means that 1 plus k whole raised to n is greater than equal to 1 plus x. Let's take this as equation number 2. Equation number 2 will be useful for proving p of k plus 1 is true. So now for p of k plus 1, we have to prove 1 plus x instead of n. I will use k plus 1 is greater than equal to 1 plus instead of n. I will use k plus 1 x. Okay, so now let's take this 1 plus x whole raised to k plus 1. I can write it down in this way 1 plus x raised to k 1 plus x. Okay, now see, I am using 1 plus x as it is. Now for 1 plus x raised to k, I can use equation 2. It is greater than equal to 1 plus kx. So I can write down this will be also greater than equal to 1 plus kx. See 1 plus x I have written as it is. Now 1 plus x raised to k greater than this. So 1 plus x raised to k into 1 plus x is greater than equal to 1 plus kx into 1 plus x. Let's multiply 1 into 1, 1. 1 into x, x. Kx into 1, kx. Plus kx into x square. That is kx square. Okay. Now see when I write down only the first three terms. Okay. Now so kx square. Here kx square that is positive because x square will be always positive and k is a natural number. So if I remove one positive element, then obviously the answer will be less. So I can write down that this is greater than 1 plus x plus kx because I am not written this. Okay. So and even in this step, x is greater than minus 1. So whatever number we multiply, this will be positive. So we can write down this. So now again equal to 1 plus I can take x common in both, so k 1 plus k I will take x common 1 plus k. Clear? So now I can write it down 1 plus x whole raised to k plus 1. equality, inequality, greater than equal to, equality, greater than equal to. So finally it will be greater than equal to 1 plus k plus 1 into x. I just rearrange this. K plus 1 and x later on. Clear? And that's what we have to prove. So this means that P of k plus 1 is in this equation 3. So from 1, 2 and 3 according to principle of mathematical induction, P of n is true for every n belonging to n. Clear? So this was about the course, this question. So just note it down. Now let's see another question. Prove that 1 square plus 2 square up to n square is greater than n cubed by 3, where n belongs to n. Okay. Let's see first for p of 1. 1 square plus, sorry, this is only 1 square. LHS, I will get 1 square. Okay, or let's check. LHS is 1 square. RHS, it's 1 cube by 3. That is 1 by 3. Obviously, 1 square is 1, which is greater than 1 cube by 3. So, P of 1 is 3. Okay, now let's assume that P of K is 3. Now, what does this mean? 1 square plus 2 square up to K square is greater than K cubed by 3. Okay, now for let's name this as equation 1. Sorry, that's 1. This as equation 2. Now for P of K plus 1, we have to prove 1 square plus 2 square. So instead of n, I will use K plus 1 whole square is greater than K plus 1 whole cube upon 3. Here, so now let's take this one, that I can write it down 1 square plus 2 square to k plus 1 square. Now before k plus 1 square, which will be the term? K square. So 1 square plus 2 square up to k square plus k plus 1 whole square. So now see, underline term k plus 1 square I am writing as it is. But now from 1 square plus 2 square plus k square, if I use this equation, then I must write this will be greater than k cube by 3. Instead of the underline, I had used k cube plus 3 plus k. Okay, now let's take LCM. So this will be equal to k cube by 3 plus 3 into, now k plus 1 whole square, k square plus 2k plus 1. Okay. Let us multiply. This will be equal to k cube plus 3k square plus 6k plus 3 upon 3. Now I want here k plus 1 cube. So if I solve it in rough, what I will get? K plus 1 whole cube. Formula is a cube plus b cube plus 3ab square plus 3a square b. So k cube plus 1 plus 3k square plus 3 into 1, 3. Okay. B. So it will be 3 into 1 square, it will be 3. Right? So see, I am having k cube. Yeah. I am having 3. Instead of 3k, I am having 6k. So it's greater. Instead of 3k square, yes, 3k square is that. Instead of 1, I am having 3, so it's greater. So see, what I will do, I will rearrange. This will be equal to k cube plus 1 plus 3k square plus 3k. Okay, plus 3k plus 2. So 3k plus 3k, 6k. 1 plus 2, that will be equal to 3 upon 3. Clear? Now this will be the positive term. Okay, if I eliminate this, the answer will be less than that. Means this will be greater. So what I'm writing if here this k cube plus 1 plus 3k square plus 3k by 3. Then this term will be lesser than this. So I can write down the upper term is greater than this. So this is equal to now k plus 1 whole cube by 3. Right? So this is what we have to prove. So what does this imply? 1 square plus 2 square up to k plus 1 whole square is greater than k plus 1 whole cube upon 3. So P of 3 is true. Okay, let's name this as 3. So from 1, 2 and 3, and P of n is true. According to principle of mathematical induction, P of n is true for every n belonging to n. Yeah, so note down this question. Now let's take one more question. Through the rule of exponents, ab whole raised to n is equal to a raised to n into b raised to n. Okay? Let's see for p of 1. ab whole raised to 1, that will be equal to ab. That means a raised to 1 into b raised to 1. So it is true. Hence, p of 1 is true. Let's make this as equation 1. Now let's take P of K as true. Let's P of K be true. What does this mean? AB whole raised to K is equal to A raised to K into B raised to K. Okay? Let's name this, sorry, B raised to K this. Now for P of K plus 1, we have to prove AB raised to k plus 1 is equal to A raised to k plus 1 into B raised to k plus 1. Clear? Now let's take LHS. That is AB whole raised to k plus 1. So this will be equal to AB whole raised to k into AB whole raised to 1. So now AB whole raised to K we can use for that equation 2. So what is equation 2? This will be equal to A raised to K B raised to K into A into B. This is from 2. So I can write it down this way: A raised to K into A into B raised to K into B. This will be equal to, see the base is same, so the power A raised to K plus 1, B raised to K plus 1, and that is equal to RHS. Okay, let's name this as 3. Okay, so we have proved P of 1 as true, we have assumed P of K plus K equal to true, using that we proved that P of K plus 1 is true. Hence, from 1, 2 and 3, according to principle of mathematical induction, P of n is true for every n belonging to n. Clear? Just note down this question. Okay, students, so that's it for today. Here we have completed chapter number 4, that is principle of mathematical induction. In our next video lecture, we will begin with chapter number 5, that is complex number. Okay, thank you.